This is a short tutorial demonstrating how to use the web application ShinyKGode to assess the effectiveness of time warping with gradient matching. The ShinyKGode application is based on KGODE, an R package that implements various gradient matching algorithms for fast parameter inference in differential equations. Both of these packages can be downloaded from CRAN. We illustrate the concepts of gradient matching and time warping using a biopathway model. The biopathway model describes the interaction of 5 protein isoforms S, DS, R, RS, and RPP in a signal transduction pathway, and it is available as one of the benchmark models in ShinyKGode. In the biopathway model, changes in protein abundance over time are described by a combination of mass action and Michaelis-Menten kinetics, having 5 system states, one for each protein isoform, and 6 kinetic parameters to be inferred, labeled K1 to 6. All the proteins used in this model will be represented as dependent variables in our ODE model. We now introduce the concept of time warping. A dynamical system, depending on kinetic parameters theta, has solutions subject to varying intrinsic length scales. To improve inference, time t is warped into tilde t via bijection with the objective to homogenize the intrinsic length scales. This is achieved by minimizing an objective function that encourages functional invariance with respect to second-order differentiation. The dynamical system in the warped domain can easily be obtained by applying the chain rule from standard calculus. Finally, after minimizing a second objective function using gradient matching, we can infer the kinetic parameters theta. We illustrate the concepts of gradient matching and time warping using the biopathway model. From ShinyKGode, we begin by selecting the model from the list. In the next step, we can load existing data in CSV format by clicking on the Browse button. Alternatively, we can generate synthetic data by specifying the start and end points of the time interval, 0 and 100 for this example. And in the pick field, we indicate how many time points to keep from the numerical solution of the ODE. Here we use the default value 2, meaning we keep every second point generated by the numerical ODE solver. Furthermore, we can specify the noise of the generated data, either in terms of variance or decibels. For this example, we use the default noise variance. Next, we need to specify the ODE parameters. In this example, we use the default values provided, K1 equals to 0.07, K2 equals to 0.6, K3 equals to 0.05, K4 equals to 0.3, K5 equals to 0.017, and K6 equals to 0.3. Lastly, we need to specify the initial conditions for the system states, which are to be used by the ODE solver. In this example, we use 1, 0, 1, 0, and 0. We then click Generate, and the synthetic dataset will appear on the right-hand side, plotted in the form of 5 time series, one for each state x1 to x5. This data can be downloaded in CSV format by clicking on the Download Data button. Next, to perform parameter estimation using gradient matching, we go to the Inference tab. Here, we can adjust various settings such as the choice of the kernel. We use RBF for this example. Note that a multi-layer perceptron kernel, MLP, which is a non-stationary kernel, is also available. We can also adjust a random seed. Furthermore, setting Bootstrap to on will prompt another option to appear that lets the user specify the number of Bootstrap replicates they would like to use to obtain a measure of uncertainty alongside the point estimates. We advise the user to start with a small number of replicates when using bootstrapping to get an initial idea of how time-consuming this option is for each scenario. Finally, the user can specify the initial values of the parameters used in the optimization routine. We will use the default values here. First, we want to run the standard gradient matching method, and to do that, we need to make sure that both ODE regularization and time warping are set to off. Clicking the Infer on Generated Data button will now run standard gradient matching. This also prompts a progress bar to appear in the bottom right corner, which indicates the various stages of gradient matching being performed in the background. Once the algorithm has finished running, the results will appear on the right-hand side of the page. For this example, we can see 5 time series plots, one for each state x1 to x5. In these plots, the noisy observations are shown as red dots, the interpolant is shown as a blue continuous line, the solved ODE with the inferred parameters is shown as a purple dashed line, and the solved ODE with the true parameters is shown as a gray dashed line. A table summarizing the results can be found at the bottom of the page. The first column shows the true parameters, the second column shows the inferred values, and the third column provides a robust estimate of the standard error based on the mean absolute deviation. We can download these results as a table by clicking the Download Inferred Parameters button. We can see from these plots that the interpolant cannot cope with both the rapid drop and the saturated section of the curve. More specifically, due to the rapid changes in the signal, the flat part is modeled with an unnaturally short length scale, which causes overfitting, a poor estimation of the gradient, and, consequently, a poor performance of standard gradient matching in this scenario. We can overcome the difficulties imposed by variations in intrinsic length scales by combining gradient matching with time warping. To use this feature in ShinyKGode, we need to make sure warping is switched to on. We then need to specify guessing periods for each of the 5 states in our system. In this example, all target periods are set to 200 with a standard deviation of 20, which means the estimated period will be in the range of 180 to 220. Note that bootstrapping is still set to on, meaning the estimates will also include an uncertainty measure. However, this comes at the cost of increased computational time. Finally, to run gradient matching with time warping, we need to click on the button Infer on Generated Data, which will prompt a progress bar to appear in the bottom right corner. As before, once the algorithm has finished running, the results will appear on the right-hand side of the page in the same format, plots at the top and the list of inferred parameters at the bottom. Comparing these two methods, we observe that time warping results in a dramatic improvement in the fit of the interpolant, displayed as a continuous blue line, to the data, displayed as red dots. This pattern is consistently observed across all 5 states of the biopathway system. The Diagnostics tab provides information about the optimization step performed during the gradient matching algorithm. More specifically, we can assess how fast convergence is achieved by looking at the plot of the objective function f against the number of iterations, as well as the provided R output with details of the optimization results for each iteration. We can also inspect plots showing the interpolation in the original domain, the warping function, and the resulting interpolation in the warp time domain for each of the 5 states of the biopathway model. In this short tutorial, we have demonstrated the improvement that can be obtained when coupling gradient matching with time warping. For more theoretical details about the gradient matching algorithms implemented in ShinyKGode, please consult the following references.